All right. I think we're rolling. So, thank you for joining me this evening, although it's who knows what time it is when you actually end up watching these videos. Probably late at night right before the deadline. But anyway, we're going to continue our journey down the memory hierarchy discussion. And I went ahead and looked at your quizzes from last time, and most everybody got the answers to those quizzes. The only thing I noticed is when we talk about cache hits and cache misses, everyone says, when you access the level 1 and the data is there, it's a cache hit. When the data is not there, it's a cache miss. And that is correct, but I do want to point out that um, the concept of a cache hit and a cache miss is a little bit more generic, and it doesn't just happen at the level 1. Okay, so when the level 1 encounters a cache miss, then it goes to the level 2 and requests data. And so you can have a hit at the level 2. Okay, and of course, because when we go back to this diagram, we look at, let's see, here, somewhere, there we go. As you move to levels further and further away from the processor, the cache size increases, which means the likelihood of having a cache miss actually goes down. The likelihood of having a cache hit goes up because of a larger cache. So it's a very likely scenario that you will get a cache miss at the level 1, but then when the level 1 requests that cache block from the level 2, it's more likely that that level 2 will actually have what you're looking for and will be a cache hit. And of course, the nice thing about that is that that the level 2 is still much faster. Accessing the level 2 is still much faster than going out to main memory. So even though you miss in the level 1, but then you hit in the level 2, that's still a huge savings over completely missing in the level 1 and not having a level 2 or a level 3 and having to go to main memory. Okay, so what we're going to see when we circle back to multiple level caches, we're going to see that the whole goal of adding additional levels is to reduce the penalty of the level 1. Okay, so we'll talk about that more as we go through all of this. So one of the things we talked about the last time was the modified Harvard architecture, and most everybody got that question right, that we're going from a Harvard architecture kind of at the level 1, and then at the next level of cache or memory hierarchy, which could be a level 2 or it could be main memory. Okay, we then have a unified memory, and so then we then become von Neumann essentially, and that's where it's called modified. And that allows us again to have our cake and eat it too. We at the programmer level, it can be a von Neumann architecture where the programmer doesn't have to worry about where they store instructions or data, storing them separately. They can be stored in the same memory, and uh, and then the hardware takes care of everything for us and allows us to solve that structural hazard that exists between the instruction port and the data port, okay, with a split level 1 cache. Okay, so most everyone got that. So very good. I'm finding that these quizzes and me actually staying on top of grading them and everything and reading them is quite beneficial. It gives me a lot of feedback. Actually, I mean, in some senses, maybe a little bit more feedback than I get, in class. In class, I have to go by more social cues, and as engineers, we're not good at picking up on those social cues. So, okay, we know what our different memories look like. We talked about inclusive versus exclusive. I'll talk a little bit more about a victim cache as time goes on. And then we introduced the simplest type of cache, and that's a direct map cache. Okay, in the direct map cache, every block has exactly, in memory or the next level, has exactly one location that it can go to in the cache. And so in this example, um, the bottom here is probably, it could be main memory or it could be a level 2, and every block here maps to only one location here in the cache. Okay, and that's where it's called direct mapped. Now that's on one end of the spectrum, and on the other end of the spectrum is a fully associative cache. And a fully associative cache means that any block in memory or the next level of cache can go anywhere in our cache. So if we have a fully associative cache, then any of these blocks in memory here, okay, any one of them, doesn't matter what color they are, they can go to any one of these blocks, okay, here in our cache. So one thing you'll probably be kind of noticing or intuitively picking up on is the fact that a fully associative cache will more efficiently use the space within the cache, okay? Um, because direct mapped has a very rigid block placement, and fully associative is quite the opposite. Okay, so as long as there's an empty block in the cache, any block in memory can go in there. So in essence, what's going to happen is you're going to have less blocks being evicted because of the placement strategy. Okay, in the direct map cache, what's interesting, we'll talk about eviction here, is let's say that that this particular block here is accessed. So then what the cache is going to do is it's going to so again, the requests go to the cache. The processor requests this particular block to the cache, and then the cache checks and says it checks its tag and the valid bit, checks to see if it's in there, and if it's not, then it goes out to memory, and then let's say it pulls this one in, right? Well, then a little while later, the processor then accesses this block. Okay. Well, what's it going to do with this other block? Well, it's going to evict it. It's basically going to bump it out, and it's going to replace it with this new block. And the reason is because there's only one location in the cache where this new block can go. And unfortunately, it happens to be in a location where we already have a block of memory. And so that prior block of memory is evicted. Okay? And so naturally, with a direct map cache, we end up with a lot more blocks being evicted. Okay, and when we talk about the different types of cache misses, that specific miss, when we come back and access this first block, well, now there's going to be another cache miss because we had the second block come in and we have to evict the second block. That is a conflict miss. Okay. And so we'll talk about that a little bit more as time goes on. Okay. All right. We also showed a simple hardware example. Okay. And in this particular instance, every cache block contains only one word, one processor word, or a 32-bit word, and there's 1024 blocks in our cache. Okay. Because there's 1024 blocks in our cache, that means we have to have an index of 10 bits. Just to relate back to this diagram, these are our indexes. Okay, so up here at the top of our cache, and that index is like an address into the cache, and it allows us to address a specific cache block. Okay, so we take a portion of our word address and use that to index the cache. That's the beautiful thing about direct map caches is their rigid block placement strategy makes it very easy and very fast to determine whether that block that you're looking for is in the cache. Because when you're supplied with an address, you just simply pull out the index from that address, go look at that block, and see if the tag compares. And if it does, then you've got a cache hit. If it doesn't, you've got a cache miss. Okay. All right, so let's go back to this example here. So again, we take the lower 2 bits of our address, because this is a word address or a byte address. The lower 2 bits is our byte offset, and our cache doesn't even care about that. Okay, the processor cares about that, but our cache doesn't. So we don't even send those lower 2 bits to the cache. Okay, the cache cares about the upper 30 bits, okay, and specifically it pulls off the next 10 bits here as our index. And because of that rigid block placement strategy, it uses that index to select this specific block or cache line. Remember, I use block and line interchangeably. And then from that, it reads the tag, and then it takes the remainder of the address and uses that as the tag, and it does a comparison with the tag that was previously stored in the cache. And then if the valid bit is asserted and the tags compare, then we have a cache hit. Okay? And in which case the processor then grabs the data that's here. Okay? If not, there's a miss, and the cache controller has to go and access the next level of the memory hierarchy. Okay, so it would go either to the level 2 or to main memory, depending on how many levels it has. Okay? Pretty basic. Now, this is an unrealistic example because each cache line only holds 32 bits of data, so it only holds one word. As we're going to see in future slides, we extend that to a more realistic example where the cache block actually holds multiple words. Again, allowing the cache block to hold multiple words allows us to take advantage of spatial locality. Okay? Most everyone answered the questions about temporal and spatial locality correctly, so that's good. This cache, if it only held one word per block, it would still take advantage of temporal locality. Okay. And of course, as we're going to see later in some graphs, there's trade-offs. You can't just make the cache block arbitrarily large, because at some point you're going to not have any more spatial locality, and you're actually going to be hurting your temporal locality. So we'll talk about that later, so don't worry about that. Right now, what I'd really like to do is I want to walk through an example that's in the book, and so if you have your textbook, you can look at this example. It's on page 386 and 387. Okay, we won't go through this whole thing because it could take quite a bit of time, but we will go through just a couple of examples, and this is actually accessing data in our cache, and so it'll show us how this caching mechanism works. Okay, so normally I do this on a big whiteboard, and so this is a little bit of an experiment. We'll see what we can do here, and I probably should have maybe created a slide. Actually, that would have been good, is if I actually created a slide with this in here. You know what? I'm going to pause the presentation, and I'm going to go ahead and modify it, and that'll save us some time here. Okay. All right, back again. I went ahead and created a table in LaTeX that we can go ahead and annotate, and so this should speed things up and hopefully keep this example fairly clear. Okay, so we're going to start out with a blank cache. Okay, so that means there's nothing in our cache. So what that means is that each of these valid bits are going to be 0. Okay, that's supposed to be a 0 there. So 0, 0, 0, 0, 0, 0, which means none of these cache lines are valid. Okay, so in a completely hardware managed cache, when the cache comes up, the cache controller will zero out all of these valid bits. On a cache that's in a RISC processor, there's actually an instruction that allows the cache, the processor to invalidate lines of the cache. And so for like ours, we have an instruction cache, and so one of the startup routines that is done before you even hit main is to go invalidate all of those cache lines, which essentially zeroes out all of their valid bits. Okay, so everything starts with the valid bits zeroed out. Okay, now the first access, okay, that the processor references is decimal address 22. Okay, so I'm gonna just write up here, and I'll be continually erasing these. So 22 base 10. Okay, in binary that's let's see, 1 0 1 1 0. Base 2 rather. Okay. Dimensions of the cache. Of course, it's an 8-entry cache, which means there's 3 bits of index, right? Because 2 to the 3 is 8. Okay, so again, this is a toy example. Our addresses are 5 bits in length, which we can see here. Okay, and for now, the references that you see here are uh, uh, word references. In other words, so the lower 2 bits, remember, in our byte address, they've already been chopped off. Okay, so this is the next significant bits above those 2. So when we say decimal address 22, that's the word 22. Okay, not byte 22. You multiply that by 4, and that would get your byte address. And then the other thing is this. Well, okay, so I don't want to get into too much detail here. So if we have a 5-bit address, and of course remember it's minus the 2 lower bits have been chopped off, and and each cache line holds a single word. Okay, so again, this is a toy example, um, and so that means that we will take the lower 3 bits of our address and use that as the index, okay, into the cache. So when we get a reference 22 base 10, the binary is 10110, okay, and so then that references our 110 index, okay, um, which is right here, okay. So it's this particular one, okay. And so initially we look, and the first thing we can look at is the valid bit, and we see that the valid bit is 0. Okay, so that indicates that because this is a direct mapped cache, that's the only location that this block could be located. Okay, then because that one location is invalid, that means we immediately have a cache miss. Okay, so there's a cache miss. Now there's a table on 386 that you'll see that they fill out. Okay, so if I had more virtual whiteboard space, I could be filling. I guess I could have added another page here and be filling that table out. But the table is nicely filled out for us already on page 386. We're just going to go through the cache and see how stuff is added to the cache. Okay. So again, initial state, everything's invalidated. Okay, then we encounter this reference to word 22. Okay, we break down the address. We take the least significant bits of this word address, and that gives us our index. We look at the cache block in that location, and we see that it's invalid. Okay, so we have a cache miss. So the cache controller will go out and retrieve that block, and then it's going to go ahead and it's going to fill in that block. So first of all, it needs to put the upper 2 bits, the remaining 2 bits of the address, in the tag. Okay, so that's our tag 10. That will allow us to differentiate between other blocks in memory that also map to this one location. Because it's a many to one mapping, we know that there's going to be aliasing to that same block. Okay, and then the data will be mem 22. Okay, I'm just going to put that notation there. Okay, and then finally we need to set our cache line as valid. Okay, all right. Let's clean things up here a little bit. All right, the next reference we get is 26. Okay, so let's look at that. Okay, so again, these are word addresses. 2610 is, and we break that down into binary, and it's 11010. Okay, base 2. So the lower 3 bits is 010. Okay, so 010 is right here. Okay, again, we see that its valid bit is 0, so that means that there's a cache miss. Okay. All right, so we're going to go retrieve that block, and we're going to write the tag as 11. Okay, and the data is going to be mem 26. Okay. And our valid bit is now asserted. Okay. So now we actually have two valid cache lines in our cache. And the rest, of course, are invalidated. Okay. All right. Let's see. Moving on. We get a reference to 22 again. Okay. So let's just go through the motions. Okay. Just so you get the point. Okay. So 22 base 10. Okay. So in decimal, that's 10110, right? Okay. And we look at the lower 3 bits of this word address, and that's 110. 110 is here. We look. Oh, look. The valid bit is asserted. Okay. So that means there's a valid cache block stored here. Now the next question is, do the tags match? So from our address, the tag is 10. We read the tag from our cache, and it's 10. So they do match. So that is our first cache hit. Okay. So we have a cache hit. Okay. The next reference is 26. Okay. So I won't go through that, but you know that the same process is going to happen. Okay. 26. We know that's in the cache. Okay. And so there'll be another cache hit. Okay. And again, if we were filling out this table, we would in the third column we would put whether there was a miss or a hit. Okay. So far we have 2 misses. Okay. And 2 hits. Okay. All right, the next reference we get is 16. Okay. And 16 is 1, 0, 0, 0. Okay. 1, 2, 3, 4, 5. Yep. Okay. All right, lower 3 bits. That's this index. Invalid. We're going to go out and fetch. Okay. Okay, so then we'll put mem16 here. Okay. And then our tag is going to be 10, and the valid bit's going to be asserted. Okay. All right. Then we have 3. I hope that some of these examples are kind of silly and they don't have anything interesting. Like what I'm considering interesting here would be an eviction, and so I'm assuming this example has an eviction. I do these examples and then I usually modify them, and I don't circle back and keep notes. I really should keep notes of my lectures from the previous years, because then I would know, oh yeah, this was a stupid example and didn't actually have a conflict miss. So if it doesn't, we'll generate one. We'll make one up on the fly, which is what I do all the time. Okay, so this is the same thing. Our index is 001. We see that it's invalid. Okay, so we're going to go out and retrieve that block. And in this case, our tag is going to be 00. Okay, and we're going to put mem3 here. Okay, and we'll change this this valid bit to be asserted. Okay. All right. Real quick, because I gotta keep remembering to interject these quiz questions. Quiz question. Okay. All right. Define what the index, the tag, and the valid bit do in a cache. Okay. So that's the index, the valid bit, and the tag. Identify what they do, and that's basically what we're doing. We're going through this example. Okay. All right, then the next reference is 16, okay? So, obviously that's going to that's going to hit, because we know we just put 16 in there. Okay, that's what's here, okay? And let's see. No, this is a completely stupid example. There is no conflicts, okay? So let's go ahead and come up with an example where there would be a conflict, okay? All right. Let's say that we're going to have to do this in reverse, okay? So let's say we're accessing 001 as our index, and we actually, the tag is 1, 1. Okay. So this particular example, let's see, 1, 2, 3, 4. That's basically, that's 15, that's 30, right? Is this 30? Base 10? Sure, right? Yeah, because the way I do this is I look and I say, okay, there's all the four upper bits are set. So that would be 15 if the 0 wasn't there. We add the 0, which essentially left shifts it, which multiplies it by 2, and we get 30. Okay. All right. So let's say we access memory location 30. Okay. So we're gonna come in here and we're gonna look and we're gonna say, oh, let's see, the index is 110, which is right here, and the valid bit is set. Okay, so we're good so far. And our tag is 1, 1. So we're going to pull the tag from that particular cache block, and we see that it's 1, 0, so the tags don't match. So now we have a miss. Now, let's pretend this is a read-only cache. So the data in that in the data section here was not modified. Okay. So, and I'll get to that. I have slides about writing to a cache. We'll talk about that later, but right now let's just not assume that happened. So then what we're going to do is the cache controller is just simply going to go out, and it's going to retrieve memory location 30, and it's going to evict memory location, what was there? 22. Okay. So 22 was evicted, and again, let's just assume we didn't modify it. If we modified it, we had to actually write the modification back to the next memory potentially, but we'll talk about that in a sec. And then we go ahead and we go ahead and modify the tag to be the new tag 1, 1. Okay. All right. So that's a cache miss. Now that's a conflict miss specifically. And I'll identify the different types of cache misses in a minute here, but that was a conflict miss. Compulsory misses are initial misses that, so all the misses we've had up to this point before this example were compulsory misses, and then I just showed you a conflict miss. Okay. All right, now let's say we come back and we get 22 again. Uh-oh. So we just evicted 22, and we pulled in 30. Okay. Well, now we're going to try to reference 22 again. Okay. Well, what do we have to do? Well, we go over here, we check the index, like, this is the block, we check the valid bit, yep, it's valid. We look at the tag and it's 1, 1, well, our tag is 1, 0. So it's a miss. Specifically, it's a conflict miss. So what are we going to do? We're going to evict memory location 30, and we're going to bring back in memory location 22. And then we're going to modify the tag again. Okay. So tag is 1, 0 now. Okay, so what we're going to see is that if our processor continues to access 30 and 22, we're going to have thrashing. Okay, and so we're going to continually have conflict misses. Okay, so at this point you're probably wondering, well, how in the hell does this even work? Okay, well, one thing I want you to keep in mind is that this is a toy example and there's only 8 entries. If you had an 8 entry cache, you would have a lot of conflict misses. But remember that we may actually have 512 to 1024 or even more entries in our cache. Okay, that drastically brings the probability of these conflicts down. Now, that being said, we still do have plenty of conflict misses with a direct map cache. Okay, think of a fully associative. See, what's interesting is we're evicting cache blocks. Okay, when we still have a number of cache blocks empty. Okay. We have 1, 2, 3, 4. Our cache is only halfway full, and because of the rigid block placement strategy, we're evicting blocks. And yet we have 4 entries empty, completely empty. Okay? Think of it like parking spaces, right? Let's say everyone had an assigned parking space and they absolutely had to park there. But even worse, it wasn't just assigned to you. Okay? It's assigned to each person, each parking space, 4 people are assigned to, right? Okay. And even though the parking space next to yours is empty, you can't park there. Okay. You have to push the other guy out of the way and park there. Okay. And then the other guy will push you out of the way. So you're going to continually do that. Okay. And that was that's one of the major disadvantages with a rigid block placement strategy like um, uh, direct mapped. But one of the major advantages is it's super simple. Okay, we already looked at a hardware example. It's very easy to make a direct map cache. Okay, and in fact, when I taught the graduate version of this class in Texas, the last lab they actually implemented an instruction cache and they got it working. So it's not all that overly difficult. Okay. Just want to remind you these are word addresses, so they're the lower 2 bits we don't even show, but keep in mind they're there. Okay. All right. So and the cache isn't terribly concerned about those low. It doesn't care about those lower 2 bits. Okay. Okay. Um, and that's not 100% correct. I always have to throw in these caveats when we talk about writing. But no, yeah, that is well, okay. So what's complicated about a data cache is it has 4 write enable signals that allow you to only modify certain bytes within a word. Okay, so there's ways of getting around that, or you can either do a read modify write, so the cache reads that data into a buffer, you modify the data and then write it back out, so you're still writing at a word granularity, or you can have byte enables supported with your cache, in which case it cares about those byte enables. But that's getting to more advanced issues. We won't worry about that for now. Okay. All right, so block size. So far in our examples, we have only had 1 word per block. But I mentioned this thing of spatial locality, where there's a high likelihood that if you pull in one piece of data, okay, you're going to use the data around it. Okay, in this whoops, I don't know what I did there. Okay. I don't quite understand the gestures. I was just trying to flip to the other slide and I did some weird gesture that the computer misinterpreted here. Okay. All right. So, that reminds me though. I was answering the discussion board. Thank you for posting stuff on the discussion board. One of the questions that was asked, and I provided the answer to this, was if we've learned a better way to write VHDL or Verilog, can we resubmit our labs? And it's like, absolutely. I mean, I haven't even graded any of your labs yet, which I feel really bad about, truly do. Um, yeah, if you find a better way, do resubmit. Okay. Um, okay. And let's see. That derailed me here a little bit, but oh yeah. So each of these memory references were just single words, and so uh, when we when we had a cache miss, we would only bring in that 1 word that was being requested. Okay, but but because of spatial locality, okay, um, we have a high amount of compulsory misses. Okay, compulsory misses are those initial misses that we have when the cache is cold, okay, or empty. And so and we use the term hot and cold. Like these structures, just like the branch predictor, have to warm up. Okay, and so as time goes on, the cache fills up, and we refer to that as warming the cache up. Okay, it's kind of a. I think it's a dated analogy back to the automotive industry. You know, where when you start up a vehicle, it doesn't run optimal while the engine's cold, and then as the engine warms up, gets up to operating temperature, then the vehicle runs at much better. You know, its full performance, and so that's the same with these structures. The cache when it initially starts out and it's empty, it's not performing very well. You saw that we had a number of cache misses. In fact, this little example we went through, there were more cache misses than hits, and the reason is well, first of all, you know, the cache initially started empty. Okay, so it was cold, so it wasn't performing very well. But then you know, the second problem is it's a very small cache, so we had some conflict misses, and then also you know, it's direct mapped, and then also we're not taking advantage of any spatial locality here. Okay, okay. So by having more than one word per block, we take advantage of spatial locality, and we end up decreasing our compulsory misses. Okay, and we also decrease the conflict misses, which, you know, it's like, well, that doesn't make a lot of sense. Um, well, you know, if you think about it, like with an instruction cache, when you end up having conflict misses, that's usually when you have like a procedural call. Okay, so and same with the data cache. When you have a procedural call, you may end up having conflict misses. Caches are large enough that within one procedure, if you execute the same procedure over and over again, or a small uh, number of procedures over and over again, you're going to have very few cache misses once the cache warms up on the instruction cache side. Data cache side is a little different, but as we'll talk about more as time goes on. But when you end up when you initially have a procedure call, you're usually branching or jumping to a fairly new location. I say fairly new because maybe you had called this procedure a while back, but it was quite a while back, and so the cache has since been flushed out and has other procedures in it. Well, then what will happen is you're going to have a whole flurry of cache misses, and they're considered conflict misses because that procedure is mapping to the same cache blocks as a prior procedure that you had accessed. Okay, and so you're going to have a whole string of conflict misses as you replace the procedure that was there with the new procedure. Now, of course, things don't work perfectly at the procedural level. You may end up replacing only part of a procedure, um, and then and then leaving the other part still in cache. And then if you go to execute that other part, then part of the procedure will already be in cache, but then when you might encounter the part that got replaced, and then you'll have to go and pull that in. Okay. But again, what you want to do is you want to pull more than one block in, especially with procedural calls and, you know, with instructions and everything. Because if you think about how, you know, a procedure call works, is you have a whole series of instructions that are all sequentially located, right? And then of course you'll have some loops in there, but um, you know, the larger block size doesn't really help for the loops, but it helps for the sequential access. Okay. So so anyway, then you'll take advantage of spatial locality and bring in more than one block. So then what you would end up doing is all those initial cache misses that we had in our prior example, you might consolidate down to one or two misses. So now you're talking one or two misses as opposed to, you know, 8 or 9 or whatever. You know, I'm just making numbers up here. And of course, the other thing you're doing is you're taking advantage of the bandwidth in the next memory up, because the way memory is designed is, remember, you access memory locations. You know, they're actually stored in rows and columns, and so when you first request a block from the next memory up, you know, whether it be a cache or memory, um, you're going to pay a large penalty to access that row. But then once you've accessed that row, then accessing words within that row is much faster. Okay, so that's where you're going to take advantage of that improvement in performance, okay, by not just accessing the requested block, but accessing its neighbors, nearest neighbors, and in block size granularities. So if the block size is fairly large, you may access a decent percentage of that overall row. So anyway, then again, there's more there. That's taking advantage of bandwidth over latency. Okay. All right. So let's extend our prior example to now have a cache block of 64 bytes. Okay, 64 bytes. If it's a 32-bit word size, is 16 words. Okay. So um, now we have 16 words per block. Okay, and that means we're going to introduce another part of the address, which is the block offset. Okay, and I'll show that in the next example. Here we go. Okay, there's our byte offset, the lower 2 bits. Remember, we just kind of ignore those. The cache doesn't concern itself with the lower 2 bits. The processor cares about those lower 2 bits, but the cache doesn't. Okay, now we have the next 4 bits is our block offset. Okay. So it's labeled here, and so it's 4 because each cache block has 16 words. Okay, so each cache block has 16 words, which means we need 4 bits. Okay, to select from those 16 words. Okay, and so yeah, 'cause 2 to the 4 is 16. Okay, now in our previous example, we had a very narrow, long cache, or dimensionally, right? We had 1024 entries, okay, and each or 1024 blocks, and each block had 1 word. Now we have 256, okay, blocks, okay, and each block has 16 words. So what's interesting is our cache size is the same. Okay, is that right? Let's see. Is it the same size? Oops, there, I did that again. Because we had 1024, so 1024 words. Oh no, they also increased our cache size. Oh, yeah, this cache is actually 4 times the size. Oh, well, I take that back. I thought the example was the 2 examples had the same cache size. Well, okay, so they don't. They have different cache sizes. If you wanted to make them the same cache size, uh, you could either say, hey, I've got 256 cache blocks, and I've got 4 words per block, right? If you had 4 words per block and 256 blocks, you would have the same cache size as 1 word per block and 1024 blocks, right? So it'd be 1024 words, which 1024 words is each word is 4 bytes, and so that would be 4 kilobytes. This example here, though, is a 16 kilobyte cache. When we don't count the tag as part of when we say, oh, it's a 16 kilobyte cache, we're counting just the data store, okay, which is this part here, okay. So in this case, we have 256 entries, cache blocks, 256 blocks, okay, and 64 kilobytes per block, okay. So uh, so this is a 16 kilobyte. Oh, whoops! I was thinking that doesn't make any sense. Whoops. Okay, it's okay. Go away. Thank you. Okay, 64 bytes per block. Okay, that makes a little more sense. Okay, so this is a 16 kilobyte cache. Okay, because 4 bytes, 4 divided by 64 is 16, right? And 4 times 256 is 1024. 1024 is 1K. Okay. Okay. All right. Continuing on. Let me erase some of this so we have a little bit of room to. So we have this byte, this block offset. Okay. And then the next 8 bits is our index. Okay, right here. And so that makes sense because we have 256 blocks. Okay, so 2 to the 8 is 256. Okay, so we'll use the next 8 bits after the block offset to select the particular line. Okay, now just as we did before, each line has a valid bit. Okay, now what's interesting is that valid bit is for the entire cache block. Okay, all 16 words or 64 bytes of it. Okay, and we have a tag. Okay, now in this case, our tag is 18 bits. Okay, because it's a bigger cache. Okay, this cache is 4 times the size of our prior example, and so the prior example used 20 bits of tag. This one uses 18. Okay, because more of the bits are being used in the index and block offset. Okay, the prior example had no block offset. Okay. Okay, so and this tag is for the entire block. Okay, so again, because we replace blocks at a time within our cache. That's our granularity is at the block level. So uh, you can see that as you increase the size of your block, you actually increase the likelihood of conflict misses. Interestingly enough. Okay. Okay. So then you use the index to pick the particular cache block. You check the valid bit. Is it asserted? You check the tag. Do they match? And if they do, then you pull that entire block out, and then you use the block offset in conjunction with this mux to select the particular word that you deliver to the processor. Okay. And now if there was a miss, okay, if the tag didn't compare or the valid bit was not asserted, then you would go to the next level of memory and retrieve that entire block, which is 64 bytes for this example. 64 bytes is a common block size, and we'll see why in a second here. I've got a graph that shows you. Computer architects like to use graphs and benchmark simulations as proof for why they're doing the particular things they're doing. So in the results section of a computer architecture paper, you're going to have some sort of spec benchmarks and showing all the different graphs and figures. Okay, so the previous example was actually, in fact, a real cache from a real processor. Okay, the Intrinsity uh, fast math processor. And so again, it was a 64 kilobyte cache. And now what they did is they actually had separate 64 kilobyte caches for instructions and data. Okay, so overall, the level 1 cache was 32 bits in size. Now, what's interesting is, so far we've kind of talked about having the instruction cache and data cache the same size. We looked at, typical level 1s on the application side of things are 64 kilobytes in size, and that's both the data and the instructions are each 64 kilobytes. But when chip real estate was a lot more scarce, you would actually see potentially smaller instruction caches. Okay, so the reason for that, I might be getting a little bit ahead of myself here, is that instruction access has lots of spatial and temporal locality compared to data access. So the cache misses that you have are much lower when it comes to the instruction cache. Okay, so again, the instruction access exhibits much more spatial and temporal locality, and as a result, instruction caches have a lower cache miss. Ooh, there's a quiz question. Why does an instruction cache typically have a lower miss rate? Okay. All right. And so in this in this example of 64 kilobytes, and so this is an much older processor, and so a processor like this would be found more in the embedded market nowadays. Okay. Okay. Oh, look. Okay, here we go. So how well did this cache work? And they showed that with Spec 2000 benchmarks, these are valid benchmarks, the cache achieved a 0.4% miss rate for instructions. That's pretty low. And 11.4 for data. Okay, so we can see there's a significant difference in miss rate between the instruction cache and the data cache. Okay, using the spec benchmarks. Okay, so again, why does the instruction cache perform better? Okay, it's because instruction access exhibits much more spatial and temporal locality than data access. Think about how instructions are accessed, right? Think about how data is accessed. Okay, so instructions are accessed sequentially with loops, and then you'll have function procedural calls and things like that. Whereas data, you might be storing the data in arrays, which will have a good amount of spatial locality. It may have temporal locality, depending if that, matrix multiply is a wonderful example of spatial and temporal locality on the data side. But a bad example, a not so cache friendly example, would be perhaps MP3 decoding, right? Where you're going to do a little bit of work on a stream of data, and then you're going to write the result out, and you're going to move on to the next stream of data. So it has good spatial locality, but the temporal locality is lacking. And then if you're accessing your data in like a linked list, that may not have the best spatial locality, because linked lists are all over the place, right? That's one of the advantages of that particular data structure. Okay, so again, data stored in arrays is going to have more spatial locality than data stored in linked lists. Okay. All right, so the effective combined miss rate is 3.2%. So how the hell did they even calculate that? Okay, the effective combined miss rate. What the hell does that mean? Well, so although instruction access has a much lower miss rate, instruction access is much more frequent than data access. So instructions access has a much lower miss rate, but it turns out we access more instructions than we do data. Okay, when I did my energy efficiency research, okay, I found that most of the energy was actually being consumed in the fetch process, fetching instructions from a 256 kilobyte ROM. Okay, I used a tool called Cacti that allowed me to estimate the energy required to access a single word from a 256 kilobyte ROM, and then I also had a 16 kilobyte RAM. And I went through the way I simulated the energy efficiency is I went and I simulated the design, and in my test bench, kind of like the test bench you all are using, I had code that would keep track of how many accesses to the ROM I had versus how many accesses I had to the RAM. And so the data port was connected to the RAM, and the instruction port was connected to the ROM. Okay, so that told me how frequently I was actually fetching instructions versus data. And even in crypto code, which is fairly data intense, okay, the amount of instructions that were being accessed far outweighed the amount of data. So, although the miss rate for an instruction cache is lower, we access the data more. So that means that the number of misses that we actually have from an instruction cache may not actually be that far off from that of a data cache. Because the data cache, yes, it has a worse miss rate, but, so in other words, the misses per access is worse, but the number of accesses is lower. Okay, so in the end, the instruction cache may end up having a larger overall number of misses. So anyway, the effective combined miss rate is 3.2%, which is far off from 11.4% and pretty far off from 0.4%. And the way that's calculated is it's actually taking into account all the number of accesses to the instruction cache and the data cache, and it's dividing the total number of misses by the total number of accesses. Okay, and so if I provided you program heuristics that said, you know, 100% of the time you're accessing the instruction cache, which turns out that's what you do basically, and 40% of the time you're accessing the data cache, and then I give you these miss rates, you would probably come up with something very close to this effective miss rate. Okay, so just to reiterate, the data access has a much higher miss rate, but the accesses to the data cache are fewer than to the instruction cache. So in the end, the number of misses, overall misses, not the miss percentage or miss rate, but the overall misses, is not too far off from the two. Okay. Now again, that's a 16 kilobyte cache and a data cache and a 16 kilobyte instruction cache. You may find that, hey, I can actually get by with a 4 kilobyte instruction cache, and maybe I'll beef up my data cache, and so put the extra chip real estate to the data cache, and you can then bring those two miss rates a little closer together. Your instruction cache will be a little bit higher miss rate because the cache is smaller, and your data cache miss rate will go down because it's a little larger. It all depends on what um, you as the architect decide is best. And that's the beautiful thing. Even yeah, maybe the 5-stage pipeline is already designed, but at the system level you can pick the sizes of caches. Okay. Okay. Oh yeah, so back to my tangent that I was talking about where I was estimating energy. So I used this tool Cacti along with the simulation to, the test bench told me the number of accesses to the memories, and then I went and I had a spreadsheet that I would then put in the number, the amount of energy per access, okay, that Cacti estimated, and then from there I could actually estimate what the cost of my memory hierarchy was, and then to estimate the energy cost of the 5-stage pipeline, I took my synthesizable Verilog, okay, and I synthesized it using Synopsys, which is an industry standard tool, against a 45 nanometer process technology, and then I went and I simulated the post-synthesis results, which is at the end you have all these different cells and they're put together, and I used Synopsys' prime time, which allowed me to essentially simulate the um, the the synthesized design, okay, and in that each cell, you know, which is kind of like a logic element within this technology library, has parasitic uh, resistances and capacitances and inductances and all of that. And the tool would then figure out all of the switching activity based on, I would simulate a chunk of crypto. And from there, it would estimate the static and dynamic power of my 5-stage pipeline. So then I would take, just like I had you do in your homework. This should sound familiar. I would synthesize that, and then I would simulate it running my crypto operation and figure out how much time I spent in that crypto operation. And I'd multiply the time by the static and dynamic power, okay, and then add in the amount of energy that I estimated from my memory hierarchy, and bada bing, bada boom, I've got now how much my overall processing system required per cryptographic operation, and then I could basically break it up, and I really should make some slide decks showing some of this research. I then put it in stacked bar graphs, which then showed for these cryptographic operations how much percentage of the energy was being consumed in the pipeline, how much percentage was being consumed by the ROM access, which was where your instructions are, and that was 256 kilobytes, and how much was being consumed in the RAM. Okay, and what I found is that more than 50% of the energy was being consumed just in the fetch process from the 256 kilobyte ROM, and then like 30% was in the pipeline, and then 10% was the RAM, so, or something like that. It's been a while since I've looked at that data, but anyway, that was kind of the breakdown, and of course it varied from different sizes of cryptographic operations and whatnot. So yeah, so what I found is that a lot of your energy was being consumed in the ROM. So well, how did I fix that? Well, I added an instruction cache, and that was kind of interesting work. It surprised both my advisor and me because when you think of caches, you think of caching for performance, but now we're saying, oh, well, there's actually a significant energy efficiency benefit to using caches, and a lot of embedded systems are sized accordingly. The sizes memories that I picked out were similar to what you might find from a PIC32. 256 kilobytes of flash, which was basically like our ROM, and 16 kilobytes of RAM, for example. That's pretty typical. And so, in a typical embedded system, if you don't have a cache, you're actually going to be spending a lot of energy fetching data from that ROM. So even though maybe for performance reasons you don't need a cache, our research showed that for energy efficiency reasons you probably want a cache. Okay. And the reason you may not need a cache for performance reasons is, as we talked about, you may slow that processor down to the speed of accessing a single word from a 256 kilobyte uh, um, flash. And and that's why microcontrollers usually run, in the 25 to 50 megahertz, range. They're not screaming fast, right? Because they don't need to be, right? They're controlling simple things, right? Sometimes, right? Sometimes they can control very complicated things. But anyway, so that's where you may not need the performance of a cache, but you could certainly benefit from the energy efficiency. Okay, moving on. That was a long tangent. Okay, so one of the questions we may ask ourselves as we're going through this is, how big should our blocks be? Okay, and well, the answer is it depends. It depends on your workload. Okay. So, for example, the size of cache block that we used for our research was 16 bytes, which is only 4 words. Okay. The example we just looked at a little while ago was 64 bytes. Okay, so 16 words. Okay. So, let's look at some data. So that's the best way, is run some benchmarks and figure out what works best. So using Spec 92 on an old DEC station 5000, probably running an alpha processor. DEC was an old computer company, digital equipment company. Okay, in the 70s and 80s, and I think, and they still had a presence in the early 90s. Well, obviously, right, because we're using, this is a fairly modern workstation, and we're using Spec 92, so this was in the early 90s when this study was done. So what they did is they went ahead and varied the block size and the cache size to determine what's the right combination of block size and cache size. Okay, and this was a data cache. So we typically, when we do these studies, we look more at the data side of things, because quite frankly the instruction cache side of things is boring. Okay, instruction access is way too predictable, way too cache friendly, too much temporal and spatial locality. So the real challenge is in the data cache. Okay, so here we see like a 4 kilobyte for this particular workload, a 4 kilobyte cache, uh, lands us, like a kind of a, I don't know, 7 to 8% depending, right? Miss rate. So our y-axis here is miss rate. Okay, so And we can see that there's a sweet spot in each of these cache sizes that's really at 64 uh, byte block sizes. Okay, now with the larger caches, so we go to a 256, the block size matters less. Okay, and like a 64 kilobyte, which this would be a modern, more of a modern cache size today. Now you might look at that and say, oh, well, that tells you that with a 64 kilobyte cache like we do today, the block size really doesn't matter that much, and that's not true. Uh, the one thing to note is this is spec 92. Okay, so let's go back and look at these miss rates here. For spec 2000, a 16 kilobyte cache is going to land you an 11.2% miss rate. Okay, let's go back to this graph. Okay, that would be this guy. So a 16 kilobyte cache, okay, running spec 2000 would land you an 11% miss rate. And that was a 64 byte block size. So you would be up here. Well, now wait a minute. Why is this particular graph saying that with a 64 byte block size and a 16 kilobyte cache, I mean, you're kind of around 3%? What's the difference? Well, the big difference here is the workload size. One of the things Spec Benchmarks does is every year they update their benchmarks. Well, I don't know if they do it every year, but they release updated benchmarks um, on a fairly regular basis, and when they do that, they increase the workload size. Okay, so from Spec 92, which was probably the second, so the first spec came out in Spec 89, and that Spec 92 was probably the next set. All the way to Spec 2000, the workload got a lot larger. When the workload gets larger, the working set of the program becomes larger. Okay, and so with the larger working set requires a larger cache. So the benchmarks have kept up with the demand that we put on our modern processors. Okay, and that's important. That's really important because if we were still using Spec 92, okay, years later, it would be giving us misinformation. It would be telling us that we could do just fine with a 16 kilobyte cache. We look at this graph and we're saying, you know what, I don't think, well, we look at this graph and we say, yeah, 16 kilobytes, would work pretty well. But if we ran Spec 2000 and it puts us up there, you're thinking, yeah, maybe I might want to increase the size of cache, right? So it's important that you use the modern benchmarks. Actually, it's more important that you use a benchmark that represents your actual workload. We didn't use spec benchmarks for our work because our workload was purely cryptographic. So we ran cryptographic operations. That's what we use as our benchmark, right? Cryptographic operations. Okay. But for general purpose processors, you want to follow the spec. There's also another very popular benchmark suite called Parsec, and Parsec is really was really kept up with multi-core, and so a lot of folks use Parsec for multi-core simulation. Anyway, so now what's interesting though is even as we changed our workload and our cache sizes have changed, the optimal block size has stayed about 64 bytes for a general purpose workload, okay, and workstation like this. So let's talk about where the increase and decrease comes as we are on either end of this 64 byte block size. So when the block size is smaller, okay, so like 32 or 16, okay, we end up with where we're not taking advantage of as much spatial locality. So when we replace a block or when we pull a new block in, okay, we increase the number of misses we have, okay, because a workload has a certain amount of spatial locality, and if we're only pulling in 16 bytes at a time, which will be 4 words, okay, we're giving up a significant amount of spatial locality, which is where that miss increases. Now, as we increase our block size, our miss rate decreases because now we're bringing in larger chunks of data. Okay, so you can think of it like filling a kiddie pool with a bucket of water, right? I mean, if you use a cup of water, it's going to take you a lot more trips to fill that pool. If you use a larger bucket, it's gonna take fewer trips, right? So that's kind of the analogy there. Well, the only problem is there's a point of diminishing return here, okay, and in which case your miss rate, this phenomenon where your miss rate is more prevalent at the smaller caches, actually starts to increase as we increase our block size, okay, and that has to do with increasing the number of conflict misses. So the conflict misses go down as we have more blocks in our cache. But if we're using a rigid placement strategy like direct mapped, okay, and we increase our block size, we now decrease the number of blocks we have, which increases the likelihood of having a conflict miss. Okay, so there's no free lunch. No free lunch. I used to have a professor that would always shout "no free lunch" during his lecture, and the funniest thing is some of us went and got a paper bag and wrote "free lunch" on it, put it on his desk. When he got in there, he got it. He's like, no, and crumples it up and says, no free lunch. But now I hear myself saying it. So there's no free lunch. You fix one problem and you cause another. So you decrease the number of misses that you have during a conflict or a compulsory, which is filling up, and then but you increase your likelihood of having a conflict miss. Okay. All right. And this is actually a nice segue into the next slide, which basically says, hey, let's classify these cache misses. Okay. And this has always been a favorite test question and quiz question for me is to list the three C's, the three types of cache misses. So in keeping with this lecture, that's your next quiz question. Okay. List the three C's. Identify the three categories of cache misses, and not only list them but define them. Okay, and so let's go through them. Compulsory. Those are the initial cache misses due to a cold cache, i.e., empty. Okay, so when the cache is cold, it's empty. You have to spend a lot of time bringing in data. Okay, and those are your compulsory misses. Larger block sizes reduce compulsory misses. Capacity misses. This is due to the cache not being large enough. Okay, and so as we increase the size of cache, we decrease the cache misses due to capacity. And conflict. That's when a cache is not fully associative. In other words, when it has a more rigid block placement. So we've seen plenty of examples of conflict misses. And the direct mapped cache has the largest number of conflict misses. Interestingly enough, a fully associative cache cannot have conflict misses. Okay, so a fully associative cache does not have conflict misses. It only suffers from compulsory and capacity misses. Okay, so the initial misses that are somewhat unavoidable other than increasing your block size, those are compulsory misses, and capacity, the cache just not being large enough. But because it's fully associative, it cannot have a conflict miss. But a direct map cache, on the other hand, can have lots of conflict misses. Now, of course, there's always a point in between these two extremes, and that's what we call a set associative cache. And I'll talk about that in a moment here. Okay. All right, so back to no free lunches, reducing cache misses. We can increase the block size to reduce compulsory misses, okay, and that's because, it's that bucket analogy. We're filling a kiddie pool with a bucket rather than a cup, okay. And so we increase block sizes, we decrease these compulsory misses. Okay, we can increase the cache size to reduce the capacity misses. And as Moore's law continues, that's or continued really past tense. That was the easiest, best improvement they could make. Right? Is they have more chip real estate, so they just start beefing up the caches. And that's, and moving them on chip, moving them from off chip to on chip, which means access is faster, and making them larger, which reduces the number of misses. Okay, so that reduces the capacity misses, and then we can increase the associativity to reduce the conflict misses, and I'll talk about how we increase associativity in a second here. No free lunch. There it is. I like that. I love that statement. Okay. So it was basically saying, well, hey, as we increase the block size, we can increase conflict misses. Okay. And we also increase the time to handle a miss, so our miss penalty. Because our miss penalty is the amount of time it takes for the cache to go retrieve the entire block. Well, if the block is larger, it's going to take more time to retrieve. Now, albeit we have the advantages of bandwidth and everything, so it may not be that much larger, right? A cache block that's twice the size will not double the miss penalty. In fact, it may only increase it by a fraction of a few percentage points. Okay. All right. So increasing the cache size, well, that requires more area. Okay. And the other thing that does is that slows the cache down, which decreases our access or increases our access time. Okay. So, and that's why I mentioned that we still don't see uh, level 1 cache is larger than 64 kilobytes because the level 1 cache has to run at the speed of the processor. So really, level 1 caches, we don't see them larger than 64 kilobytes. Okay, so what we've been doing is we've been sandwiching multiple levels between those two, between the level 1 and the main memory. Okay, increasing the associativity, which we haven't really talked about what we mean by that, but just bear with me for a moment here. It increases the cache complexity and it slows the cache down slightly. Okay, we're going to see that in a moment here. Okay, so what about writes? Okay, I need to take a little break here. We may even be out of time, but I ran out of water, and I'm going to start going hoarse if I don't drink some water here. Okay, well, lucky for you, I took a break and realized that I'm actually over time. I don't know where the time goes. These lectures just seem to fly by. Well, for me at least. They may drag on for you, but anyway, so we'll when we come back next time, we'll talk about writes. So far, we've only talked about reads, and we want to talk about how we treat writes. So what do we do when we actually modify the data in a cache, and how does it affect the next level up, which either is memory or another cache? Okay, so we'll continue our memory hierarchy discussion next time. In the meantime, I hope you all are staying healthy and happy. I believe your lab is due tonight, um, and I need to actually work on releasing the next lab. So in the next day or so, I'll go ahead and post it, and yeah, then at some point that'll be your last lab. So I'll post your last lab, and then yeah, and then we're gonna have one more homework, and we have to get a little bit further into chapter 5 before I can release that. And then we'll have our final exam, and the final exam will be take home, just like you did already. Oh, which I did look at your exams. I haven't graded them yet. I really like to get to grading them as soon as possible, but I'm sitting on a committee for a thesis defense, so I have to read a thesis in the next day or so. So once that's done, and then I'm also on another committee for work during a design review, so I got to review a bunch of material there. So anyway, big old sob story here, but hopefully by the end of the week I'll be able to go through, grade your exams, and post the solutions. So anyway, stay healthy and happy, and give me feedback on these lectures if you want. Speaking of feedback, I got an email that nobody has filled out the evaluations for this class. And maybe you're like, well, honestly, you don't want me to fill out the evaluation for this class, and that could be. But that's okay. You know what? If the evaluation is super critical, that's okay. I'll learn from it, right? So please do give me some feedback. It's anonymous feedback. I don't know who the hell even writes it. So give me some feedback on the online presentation of this material. And also, I mean, we met for class, for a number of lectures before this whole COVID-19 thing hit. So, if you can think back into your archives of how those lectures went, and the labs, go ahead and post that information. So, Well, provide the evaluation. Don't post it on the course discussion boards or anything. I mean, you can, I guess. That's okay. All right. Anyway, have a good evening.